From their first, or like one of their first series called Detective Comics.
Detective Comics, so that was the first one.
DC Comics, so it's Detective Comics comics.
So it was Detective Comics, and then Action Comics, and then DC Comics.
What does DC stand for?
Detective Comics, maybe. Is that what Wikipedia said? Okay. All right. So yeah, back to work. Again, so Ohm's law is usually written V equals IR, but it really should be written I equals V over R, because what it means is if you have a potential for charges to flow, they're going to flow, and R is their resistance to the flow. So the greater your potential, the more current you're going to have, but the greater resistance, the less current you're going to have. I is current. I is the flow of charge. In other words, it is the rate of charge movement. Question? Okay. So this is the way Ohm's law should really be written. Again, Ohm's law, we say V equals IR, but again, it's not really Ohm's law, it's just a formula. Ohm's law is actually something we'll get to a little bit later. But when you're talking about how current flows when there is a potential between where the charge is and where the charge wants to go. Kind of like a waterfall. If water's on top of the cliff and it has the potential to fall, it's going to fall. Okay, make sense? And the bigger the potential, the further it will fall. And the faster it will fall if it's going to speed up.
So is that like how it hits its velocity?
Until it hits its terminal velocity. Yeah, what?
It's like a height or just a
Kind of like a height, yeah. We're going to use, the water analogy actually works pretty well. V would be like the height of the waterfall. R would be rocks in the middle of the waterfall. As it comes down, it hits rocks and slow them down. So R, resistance, slows things down. I, current, is the flow of charge. And V is the change in, or the difference in potential that allows the charges to flow in the first place. Okay, so far so good?
Yeah.
Next really important formula is P equals IV. Okay, P equals IV. Power equals current times potential. And this is just one of those crazy formulas that when you do it all out, it's like, oh, it ends up in a watt, which is great. So we're going to use these a lot in the circuit lab, which we will do maybe tomorrow, maybe Tuesday, depending on how I feel tomorrow. Okay. So there are two types of circuits we're going to learn about: DC circuits and AC circuits. You only need to know about AC circuits. You don't have to do anything with them. Okay. Everything we're going to be doing is DC circuits. Okay. The only difference is AC circuits, the water goes up and down on the waterfall. DC circuits, it goes one way.
Oh, the game is like, we're going to be more like a lazy river.
No.
So basically, since the electrons move, the electric fields move the speed of light, Tesla said, well, if you could change the field, alternating it back and forth, then the charges would go back and forth. Which would be great. So that's what happens. In an alternating current, charges go back and forth 60 times a second. Forward, backward, forward, backward, forward, backward, forward, backward, 60 times a second.
Right?
I'm sorry?
Is Tesla smarter than Edison?
Tesla was probably smarter than everyone who's ever lived.
That's a good point.
It's entirely possible he wasn't from this universe.
What makes you say that besides this part?
Just to get your attention.
Right, but now you have my attention.
He's from DC universe. Yeah.
Sing. Okay, so batteries. Batteries are shown with a large line and a small line, or electrochemical cells, or voltage sources are shown with a large line and a small line. The large line represents high potential, the small line represents low potential. Charges move from high potential to low potential. Current, or the flow of charge, moves from high potential to low potential. So they move from the big bar to the little bar. Now, I mentioned this a little bit last week, or earlier this week. It's kind of weird. We talk about conventional current. We talk about current as the movement of positive charges. It's important to realize that it is the electrons that are actually moving through the circuit. But the conventional current is the movement of positive charges. Let that sink in for a second. Yep. For reasons I don't want to get into, dealing with electric fields and magnetic fields, we talk about the movement of conventional current, which is the movement of positive charges. mythical positive charges moving around through the circuit. In reality, it is electrons that are actually moving. But we talk about conventional current. So the conventional current moves this way, and the electrons move in the opposite direction of conventional current because they're negatively charged. Someone along the way said, it's probably easier to teach high schoolers about conventional current, which is positive, so we don't have to worry about lots of negatives canceling each other out. So that's what we do. We deal with positives. It's just easier to deal with positives than dealing with negatives that have to cancel like a negative with a negative. Yeah, the electrons are actually, again, protons cannot move. Protons can't move, electrons can, but to keep things simple, we use conventional current, which is positive. End of class. Okay. You get to go at the end of class. All right, let's, questions? Oh, yeah. Well, that's third. Give me any questions right now. It says review because I truncated a lecture and put this in here. It's actually not. So, current electricity. This is not a review. This is actually new stuff for you. Current electricity is the constant flow of charge. And it is defined as charge over time. So, current, which is given the letter I, is defined as the amount of charge over how long it takes for that charge to move. If you like triangles, you can put triangles in front of them too. Current is defined as charge divided by time. How much charge you get over how long it takes. So a coulomb, which is a standard unit of charge, traveling through a point for 1 second, the standard unit of time, exerts one, or is 1 ampere of current. Does that make sense?
So current
is measured in amps.
current equals two different
We're
things.
measuring something that's measured.
No, it's always a charge flow. Yeah. Oh, absolutely, yeah.
What is that?
So, yeah, I equals Q over T and I equals V over R. So, if you want to set V over R equal to Q over T, you're absolutely welcome to.
What is
Because they both equal current.
What is Q?
Charge. Charge. And we're going to be using big Q from here on out because big Q represents flow of lots of charges. When we're using Coulomb's law for K Q1 Q over 2 over T squared, the little q usually represents a charge. Big Q usually represents charges.
Just like that.
Charges.
A bunch of little.
A bunch of little charges cruising along. So again, usually, and not everybody follows this, and even I've even encountered AP questions that they kind of break the convention. But the convention is little q is a point charge. Big Q is a whole bunch of charges. Okay.
So big Q is a whole bunch of little Q's.
Yes. Yep. Okay, so the analogy of a water pump works pretty well. So a charge or water flows through a circuit when there's a pump. The battery or the voltage source acts like the pump. It creates an artificial source or artificial difference. It's like it creates the waterfall. And then charges get pumped from the high potential, in this case 12, to the low potential, in this case 0. Yes?
And the R is the resistor.
R is resistance. R is anything that slows charge flow.
And what's the
Well, that's a good question. If you have charges cruising past a point near the speed of light, and can we remember electrons actually do have mass? So we can pretend that moving charges have energy. Well, if you slow those charges down, that energy has to go somewhere. So that's how a light bulb works. You make a tiny little tunnel for the charges to go through, and the charges go zoom. They slow down, and because they're slowing down, they're losing energy, and that energy is given off as heat or light. So anything that uses energy will have resistance. Kind of like how the wind that travels through a wind turbine. The wind turbine spins, which then sends electricity to your house so you can power your PlayStation. But by doing that, the wind that goes through has to slow down. So the electrons traveling through a point of resistance slow down, yielding their energy. Make sense? Very. Okay, so there's that. we use the word closed to mean two different things in physics. We use the word closed for a circuit to mean it's a complete circuit. The charge starts and ends at a voltage source. So a closed circuit starts at the battery, ends at the battery. We also use the word closed to mean nothing more gets added to the system. I'm reminded of that because I was going through your syllabus and I was like, I was going through your big topics like, ooh, students are able to define a closed system. A closed system is a system where whatever is in the system stays in the system the entire time. Remember the guy, like the strong man on the train? He pushes the train. He's not actually outside the system, so there's no actual additional force in the system. So for a circuit, a closed mean the charge starts at a voltage source, the charge ends at the voltage source. Okay. Give me a thumbs up if you're ready to move on. Okay, and then we'll talk about diagrams in a second. A circuit diagram is basically that. When it's really complex, it's called a schematic, but you won't have to worry about that until you go to your second or third year of college. All right, we're moving on? No, still, some of you are like, we can diagrams. No, don't. You might like write closed, start, end, same place. Start, end, same place, closed. Okay, moving on. So voltage, current, resistance. Hey, look, there's V equals IR. So voltage is the potential difference, the thing that creates the difference, the pump. Yeah.
This isn't about this. What I shot it
A
down.
trebuchet. We're working on a trebuchet.
Totally.
So I got a trebuchet about 2 months ago at a garage sale. True story. And I looked it up, and I'm like, oh, cool. So it's one of these projects that they can build with these wooden blocks. And I thought, oh, what a fun project after the AP test. And that's not going to work because they're taking like 3 weeks to do the trebuchet. But I thought it would be fun to see how it would, as a project after the AP test, how long it would take to make a trebuchet out of wooden blocks.
Are we going to do that?
No, because it takes 3 weeks. We're going to do air rockets and a couple other things.
There's more rocky.
We just shoot each other with
Yeah, but that's a good point. But they have to glue the things together and clamp them. And they have to. They can't put it. You can't put it all together at once. It's not like Legos.
More or less.
It's a trebuchet. Yeah. So a catapult uses bent ropes or bent wood. A trebuchet just uses gravity. So we can play with it. We can play with it after the AP test, but we're not going to be able to build them because one, I wouldn't be able to build this year anyway because these are actually really expensive, and two, it takes too long to glue it together. So let's get back on task. Can we get back on task?
Yes.
All right. So voltage creates potential difference. Current is flow rate, and resistance is anything that slows the flow of charge. So there you go. Like I've been saying. So don't want to spend a lot of time on this.
What
but
is the variable for current?
I. Okay, that's a good question. This is important. So we have the variable, since you mentioned it. We have the variable and the unit. The variable for voltage is volts. How cool, huh? The variable for potential difference is volts. In fact, nobody ever calls it potential difference, they just call it voltage. So the variable is V, the unit is V. The variable for current is I, the unit is the ampere, A. Named after this guy named Andre Ampere.
Okay. And then resistance is just
So the variable for resistance is R, and the unit is ohms. Yeah, omega. Capital omega. So if you flip your speakers over, you're like, hey, it says 4 omega on it. So yeah, this is pronounced ohms.
What's the reasoning for omega?
No idea. They just, at some point, they decided to start using these letters for variables. No idea why.
Both start with that.
Okay, a couple of things. This is really important, guys. When you're doing the circuit lab, both virtually and in real life, and you're going to do both after spring break, when you're putting a voltmeter, when you want to test voltmeters, you test voltmeters in basically what's called parallel. Okay? So you place the one probe before and one probe after what you're testing. Kind of like if you wanted to know how high the cliff was, how high the waterfall was, you'd look at the top and you look at the bottom, and you look at the difference. Make sense? So when you want to know voltage, you put your probes before and after what you're going to test. However, when you want to know current is flow rate, you put your flow meter in the path. Kind of like, I have a flow meter. This summer, I waded out into a river in Colorado, and to determine the flow rate, I stuck my little flow rate meter down into the river. That's the only way you can measure flow rate, is to actually have it go through the little flow meter. No, it was the San Juan.
So when you ask us on a quiz, it's like, what is the flow rate? I just say, I need a flow meter.
No, you do the math. All right, so we're going to skip over capacitors because they're not on the AP test. If you want to learn about them, I can tell you all about them. Okay. This is actually kind of fun. This is one of those things that you should just know, but you're not going to be tested on it in any kind of detail. But you should just know what it is. There's this crazy thing. Electrons have to go from molecule to molecule to molecule, and some things have more resistance as they go from molecule to molecule to molecule. But it is actually not the electrons that... Okay, imagine you had a hose. And the hose is plugged in way down there, and someone's got a spigot. So Tanner's down there, he's going to open the spigot. And then James is going to point the hose at Carson. And Tanner turns on the hose. It takes a long time for the water to fill up, right? Okay. Now, if the water comes out and he caps it right away, and you're like, okay, we're going to get Carson good. And Tanner's like, I'm sending down some water molecules. And he lets go. Is the water molecules that Tanner sends in one end the same molecules that hits Carson right away? No, they take some time to pass through. But because fluid cannot be compressed, for every water molecule that comes in one end of the hose, one water molecule comes out the other end of the hose. Make sense? Okay, electrons do the same thing. Because electrons can't pile up in conductors, every electron that comes in one end of the wire sends one electron out one end of the wire. And it's really slow. It's about 2 or 3 centimeters per second. So when I throw this switch, light comes on right away. But the current, the electrons that are stopped right here, they're cruising along, and they're going to take like 30 seconds to actually make it up there. That really slow time is called drift velocity. Drift velocity is slow. Current velocity is fast, because current velocity is how charges respond to an electric field. And charges respond to an electric field pretty much instantaneously. But the actual charge carriers move very slowly. So the electric field is lined up in one direction, and charges respond to the electric field pretty much instantaneously. But the actual electrons that are cruising through the wire move much, much slower, a couple centimeters per second. Okay, hopefully you're not writing everything down, because once again, you need to know the concept.
Drift fast.
Yeah.
Drift slow.
Drift slow, current fast. Current go fast, drift go slow.
That's what I wrote.
Yeah. Which is what you should do. If there's nothing else you get out of my class, the most valuable thing you can do is write notes in your own handwriting or in your own words.
No, just formulas. Remember formulas.
And formulas. But you should, when you go to college, if you can write notes in your own words, you understand the material. If you can't write the notes in your own words, you don't understand the material.
That's what I've been cruising on. She will not notice.
Yeah, that's precisely it. But I won't send you to college unprepared. That happened to me, and I won't transfer those scars to you. Okay, so we talked about this. Volt is a unit of voltage. Current is a unit of I is a unit of current, and power. Okay, power. Power is named after Mr. Watt. How come I know all of this stuff? James, you must go with all of your stuff.
Me?
Yes, Donegan. No, Jimmy. You must go with all of this stuff.
So sad.
You said James, but
I'm sorry.
his name is Jimmy, and so I got so
I
excited.
know, I'm sorry. I forgot sometimes you like to be called James. You like to be called Jimmy. Okay, so power is the rate of energy flow. Listen very carefully. This is the exact same power we learned about with the change in potential and kinetic energy. So power is still change in energy. Why is that important? If you have two bulbs, one of them is bright and one of them is dim, which one is dissipating more power?
This one?
The bright, it means sending it out. Okay? So the bright one is sending out more power than the dim one, because power is energy divided by time. You have two toasters, there's my toaster, you have two toasters. You put your hand in one toaster, your hand in the other toaster. One toaster is hotter than the other one. Which one is dissipating more power? The hotter toaster, because power is energy divided by time. Does that make sense? So, what you need to take away from this is brightness is analogous to power. The reason I mention this is the AP loves asking questions, which one of these bulbs is brighter? The answer is whichever one is dissipating more power. Okay? Whichever one is dissipating more power will be the brighter bulb, or the faster moving motor, or the hotter element. Power and energy they vary with each other because it's just energy divided by time. So bright, more powerful. Hotter, more powerful. Faster, more powerful. Give me a thumbs up if that makes sense to you, because that's almost certainly going to be at least one multiple choice question, maybe two. Okay, so again, power is IV. You wrote this down. It's also, if you want to put Ohm's law and power together, it's also I squared R. But I've never seen the reason why you'd want to use that instead of just V equals IV and V equals IR. But can you see that if you just said I equals V over R? Okay, so if you just set I equals V over R and plug it in there, it just becomes P equals I squared R. Okay, so if you take P equals IV and then set V equals IR into that one, it becomes V equals IIR. Or sorry, P equals IIR.
Ah, gotcha.
By just plugging that into that. Good. Every now and then you see this popping up online. I don't think it's useful. I think it's just more useful to do P equals IR, P equals IV. Okay, give me a thumbs up if you're ready to move on. Then we're moving on. Okay, resistance. Resistance is the ohms. It is named after a guy named Georg Ohm. You can call him George if you want. He's dead. And the resistance is what you get when you have one current flowing through 1 volt. And resistance of all materials is different. To calculate resistance, the formula is rho LA. Hey, let's use rho not for density, but for something else. That's a great idea. It's not density, it's resistivity. It is resistivity. And to make things more fun, things that are more dense usually have a lower resistivity. But it's still rho. So this rho is resistivity. Basically, it's the
What is that one? What is that still one?
Rho length area. Rho length area. RHO. So this rho is not density. This rho is resistivity. Basically, it's a measurement of how well the molecules can pass electrons. A high resistivity means they don't do that very well. So plastic, extremely high resistivity. Gold, extremely low resistivity. So it's a measurement of how well they can pass electrons. Which should make sense because this is resistance. If your resistivity is really high, your resistance is really high.
Wait, is it
Yeah?
more dense is less resistive or whatever because the atoms are more dense?
Exactly. And they're tend to be metallic. The most important thing in resistivity is d-block electrons will pass quite. D-block electrons will pass to each other very, very easily. And carbon atoms in an sp3 organization, like a diamond or a nanotube, will also pass electrons very easily. It's primarily the arrangement of their orbitals. So,
For chemistry.
now what does this mean? Yeah.
Why does metal conduct electricity so well? That's what you just said.
Okay, so if you remember your chemistry, it's okay. If you remember your chemistry, there is s, p, and d orbitals. Remember that? And there's also f. So the s's are spheres, the p are dumbbell shaped, the d are really long dumbbell shaped. And the molecules in the d block are so close together that their d orbitals overlap. So the electron can easily go from one orbital to the next orbital, not even realizing it's left its atom. So the d orbitals are like a big web, where the electrons are like ants traveling along the web. They can easily go from one atom to the next atom to the next atom to the next atom in every direction, just as fast as if they were spinning around the same atom. So it's called the electron C model. And it's why metals have such, basically it's why metals have the properties they have. Why they're shiny, why they're lustrous, why they're good heat conductors, why they're good electricity conductors, why